ahead and get started.
Yeah.
Is everybody here? Do we need to grab some more people? I think so. What is your tie? All right, good afternoon, everybody. It's indeed my pleasure always to introduce Zhen Leng. He's one of our top former students. He got the Mavis Award from the College of Engineering. He completed at 4.0, and I just keep going. And he did an amazing job in his publication record. He, of course, ended up working at the Hong Kong Polytechnic University. It's a top school in Hong Kong. And he received his tenure. He is now an associate professor. He's an associate editor for a journal, one of the new journals that we have as part of the ASCE. And I'm not here to list his record, but all I can say is I just summarize it that we're very, very proud of him. And we always like to see him here, University of Illinois. And yes, when he was a student, he got abused like you are, guys. So that's how it works. That's how we end up having top people graduating from this program. So without any further ado, I want just you to welcome Zhen Leng.
Thanks, Professor. Always. Every time when I see Professor, I feel a little bit excited and nervous. When I'm back here, I still feel like I'm a student again, actually. So it's indeed my great pleasure and honor to be back to ATRA, where I actually stayed for almost 7 years. Okay. So today I'm here again, and I'd like to share with you, report to you some of the research currently I am working on at the Hong Kong Polytechnic University. And to be more specific, I'm going to talk about some of our ongoing research about using the waste plastic in asphalt mixture. And before start, I would like to just very briefly introduce the university where I'm now working at, and also the research work we are currently conducting at Hong Kong. So probably some of you know that Hong Kong is a special administrative area of China, which is located in the very south part. Okay? And because of the historic reason, Hong Kong is a city known as a world city of Asia, where East truly meets West. Okay? And if you have experience, if you have chance to visit Hong Kong, you will notice Hong Kong is actually a city with mixed culture of both the West and the East. Okay? So I sincerely invite you actually to visit Hong Kong if you get a chance. I know some of you have already got experience. If not, I'd like to sincerely invite you to do that. Okay? And Hong Kong Polytechnic University, our university, is one of the 8 public universities in Hong Kong. And as you can see here, this is just an overview picture of our university. And this one, okay, which you're facing this very fancy building, is our department building. Okay? And this building is actually also part of our university, but unfortunately it does not belong to our department. But in our department, if we open our office window, we will have a good view, very nice view of this nice building. Okay? And currently, our university, Hong Kong Polytechnic University, is ranked number 95th in the world according to the latest QS ranking. And our civil and structural engineering is actually ranked number 10 in the world. And our university is also the only university in Hong Kong which offers the payment research program. Okay, so if you in Hong Kong, if you are looking for someone who are doing the payment research, then it must be someone who worked at the Hong Kong Polytechnic University. Okay. And right now, the research areas, okay, research interest of our group mainly include the two. The first is about the infrastructure non-destructive evaluation. This is actually related to my PhD work, where I was working with Professor Arkady. So we apply different non-destructive techniques, such as ground penetrating radar and also infrared for the non-destructive evaluation for both pavement and the railroad system. And the second area is about the sustainable paving materials and the technologies. Okay. So under this area, we worked on different recycled waste materials. For example, the rubberized asphalt or the warm rubberized asphalt, and also the reclaimed asphalt pavement, and also the waste plastic. Okay. And also we worked on different functional pavements. Okay. For example, we used the porous asphalt as a way for the stormwater management, okay, and also for the noise reduction. And also we did some research on the photocatalytic pavement, which is a functional pavement that can help degrade the vehicle emission. Okay. And one thing, okay, we have been working a lot on is the low noise pavement. This is very important for high-density cities like Hong Kong. Okay? Because of the high population density, actually many of the buildings actually are built right next to the roads. Okay? So how can we reduce the traffic noise, okay, caused by the tire road interaction is something we have spent a lot of effort. Okay? We worked on both low noise asphalt pavement by using technology like the porous or using rubber material, and also we worked on different surface textures for concrete pavement to optimize its traffic noise and skid resistance. Okay. And finally, we also work a little bit on different tools that we can apply to quantify the sustainability of different pavement materials and technologies. This is actually, I started working on this while I was doing postdoc with Professor Arkady here. Okay. At that time, we worked on the life cycle assessment, LCA, on the warm mix asphalt. Okay. And also, there's some other tools like the eco-efficiency analysis, which I think it's a similar tool, okay, which allow us to provide quantitative information on the sustainability, which can be used by the decision makers, okay, to make the decision. Okay. So this is just an overview, quick overview of the research we are conducting now at the Hong Kong Polytechnic University. And in this presentation, I'd like to share with you our research on combining these two waste materials, okay, the waste plastic and the reclaimed asphalt pavement. Okay. So here is just the outline for my presentation today. And I'm going to start with a little bit introduction to the two waste material we are investigating in this study, the waste plastic and the reclaimed asphalt pavement. Okay. So first of all, the waste plastic. So when we're talking about the waste plastic, first we should know what is plastic. Okay. So plastic, I think it's some material we are all very familiar with. It's almost everywhere in our daily life. Okay. But one thing we should be aware of is the plastic is actually, it's not a single material. It's a family of thousands of different materials, okay, which are designed for different purposes. Okay. So we have both the thermoplastic material and the thermoset material. Okay. For thermoplastic, for example, the PVC, the PE, or the PET, they are all thermoplastic material. And for thermoset material, we have like the polyurethane or epoxy. Right now, I think there are some research ongoing on using polyurethane and epoxy as cold binders to produce the cold mixtures. Okay. So we are now also working a little bit on that actually. But here, I'd like to emphasize that when we are talking about the plastic, it's a big group of material instead of one single material. Okay? And in this study, actually, we cannot actually deal with all the different type of material. In this study, we are now actually mainly work on one of the plastic, which is PET, okay? Which is a material that used to make the water bottles, the drink bottles. Okay. And for different plastic materials, as we said, we can use it to make different products serving for different purposes. So we have the like the plastic bottles. It's actually made of the PET material. Okay, and also we have like the plastic bags. We used to use a lot in supermarket. It's actually made of PE. Okay? So to differentiate the different plastics, I think some society called the Society of Plastic Industry developed some symbols. Okay, and I think if you have a water bottle, if you flip it to look at the bottom, you will see such kind of triangle-shaped symbols. See? So by reading these symbols, you will be able to identify which type of plastic is used to make that product. Okay? So for example, if we see number 1, okay, inside, then it always refer to PET or PETE. Okay? So for all the drinking bottles, you will see actually number 1 label at the bottom of the bottle. Okay? And here's some statistics of the global plastic production. Okay? In year 2015, okay, the total plastic production in the world is about 269 million tons, okay, which is obviously a huge number. Okay? And and just as expected, China is the country which produced the most plastic, okay, and followed by Europe and North America. Okay. And currently in Hong Kong, okay, actually waste plastic is the second largest waste category of the municipal solid waste. Okay. Probably you can guess what is the first largest waste category. Jaime, you know what is
paper?
Paper? That's not correct.
Rubber?
Flour?
From the tires? Rubber?
Not. Rubber is not as much as actually the waste plastic. The first one is actually who said food? Yes. So we need some Chinese guy here to get around food. Yeah, food waste. Yeah, food waste is the number 1. Yeah, number 1 waste category of the municipal solid waste. Okay, in Hong Kong, and I think also probably in most cities in China. I think, yeah. But waste plastic is second largest. So a lot of waste plastic produced. Okay. So according to statistics, okay, you can see how the waste plastic production, waste plastic disposal rate increased with the year. Okay. But at the same time, we noticed that the plastic waste recovery rate in Hong Kong actually keeps decreasing. Okay. This is actually some complex reason. Okay. Probably some are related to some political reasons. Okay. So, but anyhow, there's some severe imbalance between the waste plastic disposal and the waste plastic recovery. Okay. And in 2015, we can see the total amount of plastic waste is approximately 800,000 tons, but only about 10% of the waste plastic were recovered through recycling. So we are facing a big challenge of recycling the waste plastic material. Okay. So to manage the waste plastic, okay, there are 2 ways. The first is to do the landfilling. Okay. So obviously, landfilling is not an ideal method to manage with waste plastic. Okay. Because first of all, it actually decreases our land space, okay, especially in cities like Hong Kong. We are very short of the land space. Okay. So we really don't want a lot of waste to occupy our limited land space. Okay. And also, if we don't do it correctly, we may cause the land and water pollution. Okay. So because of this, the increase in recycling and reuse are not only desirable, but rather it's very essential. Okay. So to recycle the waste plastic, okay, we also have different options to do it. Okay, we might use the mechanical way or the physical way, probably just cut the waste plastic into small pieces without any change to its chemical composition and reuse it. Okay, and also we can do it in a chemical way. That means we need first to chemically change the material and then use it. Okay, or we can do it in a thermal way to just to incinerate the material to produce the energy. Okay, and in payment engineering, okay, we also want to do something to contribute. Okay, so people have tried quite some people have tried using the mechanical way to recycle waste plastic into asphalt mixture. Okay, basically just like treat the waste tire rubber, just cut them into small pieces and add them to asphalt mixture. Okay, but this actually was not very successful. Okay, so many researchers tested the mechanical performance of the mixture after they add the waste plastic. They found the mechanical performance is good. Okay, but during the production and the storage, there are two major concerns. One is there's emission during the construction process because we know for the hot mix asphalt, okay, when we produce the material, we have to heat it to high temperature, and that high temperature, if we add the waste plastic, there might be emission generated. Okay, and also the storage stability is a problem because the plastic material has very smooth surface. Okay, so such smooth surface does not allow a very good compatibility, okay, between the plastic material and the asphalt binder. Okay, so because of these two major concerns, okay, there actually has not been too much real field application, okay, of the physically or mechanically treated waste plastic into the asphalt pavement. Okay, so in addition to the physical treatment, we can actually consider the chemical treatment. Okay, but in this area, okay, there has not much been done yet. Okay, there has not much been done yet. So this is actually also one of our motivations to conduct this study. We want to see whether we can first convert the waste plastic into some different material. Okay, and then add them into asphalt mixture. Okay, so in this way, we want to overcome these two limitations, okay, of the mechanical recycling. Okay, and also we want to know, okay, after such kind of chemical treatment, okay, whether our plastic derived material or derived additive can help improve, okay, improve the performance of asphalt mixture as a modifier or additive. Okay, so that's just some very brief background on the waste plastic. Okay, now so we are switching to the wrap. Okay, so we know that waste plastic is one of the major type of the municipal solid waste. Okay, and in addition to the municipal solid waste, okay, we also have the construction waste as another type of major waste material. Okay, and in our pavement engineering, we all know that the reclaimed asphalt pavement or wrap is one of the major components, okay, of the waste produced from the road construction. Okay. And in our pavement engineering, the reuse of wrap actually has been very widely promoted by transportation agencies all around the world. Okay. But the wrap application percentage usually kept at low percentages, usually 10 to 30%. Okay, mainly due to the performance concerns, especially the fatigue performance, low temperature cracking performance, and the moisture damage resistance. Okay, because the aged binder becomes much more brittle. Okay, so we have big concerns on this cracking resistance and moisture damage resistance. Okay, so unless we use certain rejuvenators or use some soft binders, okay, usually we control our wrap percentage at a relatively low percentage. So in this study, okay, we were thinking, okay, whether we can first chemically treat the waste plastic, okay, and convert it into some modifier or additive, okay, and then we use this modifier or additive to improve the performance of the wrap mixture, especially those mixture containing high percentage of wrap. Okay, so our specific objective, okay, is to explore the feasibility of using the functionalized additives from through the chemically recycling of waste PET plastics in high wrap bituminous mixture. Okay, and we want the bituminous mixture to be more durable compared with those without the additive. Okay, and our motivations, okay, mainly include first to recycle two waste material, the plastic and the wrap simultaneously, and the second, which is actually more important, is to improve the performance of the high wrap bituminous mixture, especially their moisture damage resistance and cracking resistance. Okay, so this is what we plan to achieve, okay, through this study. Okay. So here is what we propose to do. So first of all, okay, we are going to collect the waste plastic. So as I mentioned, right now we are actually mainly working on the waste PET, which is plastic used to make the water bottles. Okay, and then we are going to chemically treat the waste plastic and convert it into some additives. Okay, we call it waste plastic additives. Okay, and then we are going to add this additive into the virgin binder, okay, to produce the waste plastic modified asphalt or binder. Okay, and then we're going to mix it with wrap and virgin aggregate to make the bituminous mixture which can be used for the road paving. Okay, so in this flow chart, okay, obviously the most important step is this step, the synthesis. Okay, this is gonna determine whether this idea can be finally achieved. Okay, so in order to in order to chemically treat the waste plastic material, we actually have many different options. Okay, so basically, if we use any chemicals to react with plastic and convert it into something new, we can consider it as a chemical treatment. Okay, so we do have many different options. Okay, and in this study, we actually selected a chemical treatment method called aminolysis. Okay, so what is aminolysis? Aminolysis actually refers to the reaction. Okay, a reaction in which an amine is a reactant and becomes part of the reaction product. Okay, so basically we just use some amine material and make it to react with waste plastic. Okay, and then we can chemically treat the composition of the waste plastic and convert it into something different. Okay, and the reason why we select this process is first, this process is considered atomic economy, and why it's called atomic economy? Okay, this is because after the chemical reaction, actually we will not lose any material, we will not lose any reactant. So everything we used for the reaction will become the final product. Okay, so the leftover we can continue to use it for the further chemical treatment. Okay, and also this process is relatively less energy intensive. We do need heat, we do need some heating for the reaction, but we only need to heat it around 80 degrees C, so not a very high temperature. Okay, and also the process is quite simple. Okay, we just need to put the two materials together and into some container. Okay, and finally it's relatively time efficient, and we don't need to add any additional catalyst. So the reaction usually just takes 6 hours to complete. Okay, so because of these reasons, okay, we selected this chemical treatment process. Okay, so here you can see what actually happens. Okay, this one is the chemical structure for the PET. Okay, and this is the amine material we used. Okay, which is the triethylene tetramine. Okay, what we call the teta. And during the reaction, actually what happens is in our PET material, we have some ester groups. These ester groups are actually relatively weak groups. Okay, so they can be easily attacked and replaced. Okay, by these amine groups. Okay, in the amine material we use. Okay, so after the reaction, okay, you will notice. Okay, the ester groups will be replaced by these amine groups. Okay, and also another change is originally the waste PET it has a very long chain structure. Okay, you notice the number N here. That means it has a relatively long chain. Okay, and after the reaction, actually we cut the long chain into short pieces. So basically we degrade the material. Okay, so two things happen. First is that we degrade. Second is we introduce the amine groups into the material. Okay, and these amine groups actually later on I will show they are actually very helpful. Okay, to improve the performance of the acyl mixture. Okay, especially their fatigue and moisture damage resistance. Okay, and this is the change. Okay, we can see from the SEM image. Okay, before the treatment, you can see the surface of the PET quite smooth. Okay, and afterwards, you can see its surface becomes very rough. Okay, and such rough surface also allow a very good mixing. Okay, good mixing between the PET additive and the acyl binder. Okay, and here's actually how the additive will look like. It's a semi-solid. It's in semi-solid state at room temperature. But if we heat it to probably around the 60 degrees C, it will become liquid. Okay, so at the mixing temperature for the acyl mixture, actually this additive can be easily turned into liquid. Okay, and because it's a liquid, it also allows us to very easily mix it with the acyl binder. Okay, so the storage stability is not a problem at all for this additive. Okay, but it is a problem for the PET material. Okay, okay, to verify whether our aminolysis process is successful, we conducted some chemical analysis through the FTIR, Fourier transform infrared analysis. And here is the spectrum of our additive. So in the spectrum, we can clearly see these two peaks, which actually belong to the amine groups. So because we can successfully identify these peaks, that verified our aminolysis process is successful. We did introduce the amine groups into the additive. So after such preliminary investigation, we decided to do further investigation. So we made such an experimental program. To run more tests on the binders which have been added the additives. To see how this additive gonna change or affect the binder's property. So what we have done is first we collect the waste plastic or waste PET, and then we use the aminolysis process to convert it into the PET additive. And also we collected the virgin binder, which is a binder with a penetration grade of 60-70, which actually corresponds to a PG grade of PG64. It's a binder without any polymer modification. And then we can produce the PET modified binder called PNB. So here it's actually P represents PET, not the polymer. And also we actually collected the field wrap samples. And then we did the extraction. To get the wrap binder. And then what we did the artificial blending. Artificial blending of the PET modified binder with a different percentage of the wrap binder. So here wrap actually represents the wrap binder. And also we have the virgin binder and the PET modified binder without any wrap binder as a control materials. So in total 5 binders. And for each binder, we conducted the anti-stripping property test, the conventional penetration, softening point, and viscosity test, and also the DSR and BBR test. And finally, we did some material characterization analysis. Okay, so now I'm just going to quickly go through the results we have obtained for each of the tests. So first is the anti-stripping test. So the anti-stripping test we have conducted is the hot water immersion test according to the ASTM standard. I assume probably many of you are familiar with test. Basically, we just first coat the aggregate with the binder, and then we put it into hot water and boil the aggregate with the binder for a certain amount of time, and then we take it out to check the surface coating of the aggregate. So in this slide, you can see the first picture here is actually the aggregate coated with aged wrap binder. You can see what happens after the test. The majority amount of binder actually was actually lost after test because of the aging, because of oxidation. So which means the moisture damage resistance is quite poor for the aged wrap binder. And for the second picture, for the virgin binder, we can see it's much better. After test, we still have made most of the binder very well coated on the aggregate surface. And the third one is the aggregate with the PET modified binder. You can see the difference. So compared with the virgin binder, it's even better. So we can hardly see any actually binder loss after the test. So in the bottom you can see the aggregate coated with the PET modified binder with different percentage of wrap binder. The first one with 15%, 25%, and 40%. So if we have 40% of wrap binder usually we can consider it as a high wrap mixture. And here, we can compare these pictures. So we can see even with the 40% of wrap binder, there's still a very good coating after test, which is actually similar to the virgin binder, probably is even better. But here, notice we actually have already added 40% of the aged wrap binder. So these tests actually are very promising, with indicating that the PET derived additive seems can significantly improve the stripping characteristic of the wrap binders. And actually the main reason actually is due to these amine groups. Such amine groups actually can serve as a bridge between the asphalt binder and the aggregate. It has good adhesion properties with both asphalt binder and aggregate. Actually, amine material also have been used in the literature as an anti-stripping additive. Actually, And following the anti-stripping test, we also did the conventional viscosity, softening point, and penetration test. So here, the plotting on top is for the viscosity. The first column represents the virgin binder. Always the virgin binder, different temperatures. And the second column, the blue column, represents the PET modified binder. And the following are those binders. Are those PET modified binders with increasing amount of wrap binder. So from this plot, we can see the trend is very clear. If we add the PET additive, we can see it slightly increase the viscosity of the binder. And if we further add the wrap binder, so as expected, the viscosity will be further increased. And for the softening point and penetration, we actually got a similar trend. For the penetration, if we add for softening point, if we add a PET additive, the softening point is slightly increased, and for the penetration, if we use the PET additive, the penetration actually slightly decreased. So all these test results indicate that the PET modified binders actually can be expected to show better performance in hot climate regions, okay, such as where I'm now working on Hong Kong. Okay, this is because it actually kind of increase the viscosity, okay, of the binder, and also decrease of the penetration of the binder material. Okay. But notice these tests are conducted at different temperatures. Okay. The viscosity increase is actually not that much. Okay, not that much. So so this actually is important regarding to the workability of the binder and the mixture. Okay. So to in addition to the lab test, okay, as researchers, we also did a little bit simulation, okay, the molecular dynamic simulation, okay, and in the molecular dynamic simulation, okay, we selected the conventional 12-component acid binder model, okay, and for the PET additive, we just use its chemical formula, okay, to build its model, okay. And through the molecular dynamic simulation, okay, we got some parameter called the cohesive energy density, okay, and we compared the cohesive energy density of the virgin binder without any PET additive, and with the 2% and 4% of PET additive. We found that the cohesive energy density actually increased about 25%, okay, after we added the PET additive. Okay. So this is actually simulation result is consistent with our softening point, viscosity, and penetration test results, okay, because larger cohesive energy density indicates the material probably is stiffer, a little stiffer. Okay. Okay. So then we also conducted the DSR test, okay, to check its rotting performance and the fatigue performance. Okay, so we all know that by doing the DSR test, we can get two important factors. One is the rotting factor, one is the fatigue factor. Okay, so for the rotting factor, okay, we have done tests on both the unaged binders and the RTFO aged binders. Okay, and in these two plots, the first column is always the virgin binder, and the second one is the PET modified binder, and the following are the PET modified binder with increasing amount of red binder. Okay. So from this test, okay, we noted that, okay, after adding the PET additive, okay, which is the second one, okay, compared with the first one, okay, in most cases, okay, it actually slightly increased, okay, slightly increased the rotting factor, but not that significant. Okay, there were some cases which are slightly decreased, okay, but the change is not significant. Okay, but if we further add the red binder, okay, if we further add the red binder, okay, we can see the rotting factor values are significantly increased compared with the virgin binder. Okay, so which means if we combine the PET additive and the red mixture, definitely we will get better. We expect to get a better rotting performance from the binder. Okay, and in the bottom, okay, we can see it's the test results for the fatigue factor. Okay, for the fatigue factor, okay, we know, okay, contrary to the rotting factor, we want to have a relatively lower value, okay, for the fatigue factor, because to have better fatigue performance, we want the material to not to be that stiff, okay, to have good fatigue resistance. Okay, so a lower fatigue value actually represents a better fatigue performance of the binder. Okay, so here we can clearly see the difference. Okay, compared with the virgin binder, which is the first one. Okay, the PET modified binders, no matter how much red binder we have added, okay, its fatigue factor is much lower. Okay, much lower. Okay, so this means we expect much better fatigue performance. Okay, of the PET modified binders. Okay, no matter with or without red binder. Okay, so through the DSR test, okay, our findings first, okay, for the PET additive, it actually its effect on the rotting factor is not significant. Okay, but the binders with both PET additive and the wrap binder are much better than the virgin ones. Okay, and for the fatigue, okay, we can see the PET additive can significantly improve the fatigue performance of the binder. Okay, so to find out the reason, okay, we also did some literature search. Okay, and here is the some of the potential reasons. Okay, we found out okay, based on our literature search. Okay, so on the top, okay, you can see, okay, this actually represents the acyl binder. Okay, in the acyl binder, we can see there's actually some group which is called the hydroxyl radical. Okay, hydroxyl radical. Okay, so similar to what we have done during the aminolysis process. Okay, if we add the PET additive, okay, the amine groups, okay, can again actually attack this hydroxyl radical in acyl binder and replace them. Okay, replace them. Okay. So after such kind of a replacement, we can see the length of the chain of our acyl binder actually is increased. Okay, because originally it just has such kind of a group, hydroxyl radical group like this. But after we add the PET additive, okay, we introduce the whole additive, okay, into the acyl binder. Okay, so such kind of replacement, okay, actually increase the length of the chain of the binder, okay, which could help to increase the tensile strength and the elastic response, okay, of the acyl binder material. Okay. So because of this, the fatigue performance of the binder is expected to be increased. Okay. So this is the potential reason, okay, why the PET additive can significantly help to improve the fatigue performance of the binder. Okay. So in addition to the DSR test, we also conduct the BBR test. Okay. Although actually in Hong Kong, usually we don't need to run the BBR test because of the very warm climate in Hong Kong. Okay. But as researchers, okay, we always need to do the comprehensive study to know how the material behave at low temperature. Okay. So for the BBR test, okay, we know we can get two parameters, the M value and the stiffness. Okay. For the M value, okay, we wanted it to be as large as possible. Okay. For the stiffness value, we want it to be smaller. Okay. To not to be that stiff, to have good low temperature cracking resistance. Okay. So if we take a look at these two plots, okay, we can see in terms of the M value, okay, after we add the PET additive, which is second one, okay, the M value is actually slightly increased. Okay, it's slightly increased. Okay, and for the stiffness value, actually the stiffness value is slightly decreased. Okay, both are actually good for the binder's low temperature cracking resistance. Okay, and if we further add the wrap binder, okay, we can see compared with the virgin binder, okay, both M value and the stiffness, there are not a significant difference. Okay, in other words, actually, it will not change the low temperature grade. Okay, it will not change the low temperature grade of the virgin binder. So our our virgin binder actually can meet the requirements at minus 12 degrees C. Okay, and after we add the PET additive and even the wrap binder, we can still meet this low temperature grade requirement. Okay, so in terms of low temperature grade, okay, we can see the PET actually has can slightly improve. Okay, but the difference is not that significant. Okay, so following all these rheological property tests, okay, we also did some chemical analysis. Okay, so here what you can see is some results from the fluorescence microscope test. Okay, the one on your left hand side is for the virgin binder. This one for the PET additive modified binder. Okay, So from this image, we can see those red dots, okay, which are relatively uniformly distributed. Okay, so this indicates our PET additive actually has a relative uniform and homogeneous distribution inside the binder. Okay, so this is actually important to ensure our binder has a consistent material property. Okay, and also we conducted the FTIR test, okay, on different binder samples. Okay, this green one, okay, represents the binder, okay, extracted from the wrap mixture, okay, which is aged binder. Okay, so for the aged binder, this one on the top, okay, we can clearly see two peaks. One corresponds to the SO double bond, and the other one corresponds to the CO double bond. Okay, these two peaks are mainly due to the oxidation, okay, of the binder. Okay, and now, okay, if we take a look at the other binder samples, okay, the PET modified binder is this dark blue one, okay, which is I think at the relatively bottom part. Okay, so if you take a look at the PET modified binder, okay, we can see these two peaks, okay, are significantly their amplitude are significantly reduced, especially for the CO double bond peak. Okay, we can actually hardly see the peak. Okay, and even with the wrap binder added, okay, this peak is actually not that significant. Okay, not that significant. Okay, so for the SO double bond, yes, there's still some peak, but it's much less significant compared with the wrap binder. Okay, so from the FTIR spectrum, okay, we notice that the oxidative peaks, okay, are reduced, okay, when the wrap binder is mixed with the PET modified binder. Okay, so this somehow indicates the PET additive even has certain rejuvenating effect. Okay, rejuvenating effect. Okay, but we still need to probably do more tests to verify such effect and find out what is the reason behind. Okay, first to verify whether this is true, and if it's true, we need to verify. We need to find out what's the reason behind. Okay, so this is actually really good. Okay, if we add the additive into the wrap mixture, it provides both the rejuvenating effect and also the serve as the anti-stripping additive. Okay, it really helps our wrap mixture. Okay. So here, just a quick summary of the findings. Okay, we have obtained so far. Okay, so first of all, okay, through the PET, through the chemical treatment, analysis process, we actually converted our waste PET material into PET additive, and we found the PET additive can significantly improve the moisture damage resistance. Okay, can serve as an anti-stripping additive. Okay, and also if we use the PET additive, okay, the writing performance is not actually changing much. Okay, but we can significantly improve the fatigue performance, okay, of the binder and the wrap binder. Okay, and also we found that the PET additive will not change the low temperature grade. Okay, low temperature grade of the binder. Okay, it even has slightly positive effect actually, and the FM image show that the mixture of the PET model binder is relatively homogeneous. Okay, and our FTIR spectrum test results indicate that the PET additive has certain rejuvenating effect to the binders. Okay, so that's actually what I have presented. Actually, just what we have done so far. This project actually is now still ongoing. Okay, so you can see I only presented some tests for the binders. Okay, so we are now actually still working on this project. Okay, so what we are now working on is to further verify the effect of the PET additive as an anti-stripping agent and rejuvenator through different tests. Okay, for example, definitely we need a mixture test to verify, and also probably some mortar test will also help. Okay, we want to verify such effects really exist. They really exist. Okay. And also, as I mentioned at the very beginning, the plastic is a big family of different materials. Right now, we only focus on the PET. Okay, and next we are going to extend the types of waste plastic to different plastics. Okay, such as the PVC and the PE. Okay, right now we are working on this actually, and also for the aminolysis treatment process. Okay, we can actually select different types of amines. Okay, in this study we picked one which is called theta, and we actually can also consider other amine materials. Okay, if we select different amines, okay, then our final product will also be a little different. Okay, and their probably modification effects to our binder will also be slightly different. Okay, so we are going to investigate different types of amine materials. Okay. And for different amine material and waste plastic, okay, we are going to further explore more potential applications. Okay. In this study, we found that it seems the PET-based additive has good anti-stripping and rejuvenating effect. Okay, so we also want to investigate, okay, whether we can produce, okay, some additives, okay, from waste plastic for different purposes. Okay, for example, as a warmix additive, okay, or as a rotting resistance enhancer. Okay, to say, depending on different amines and plastic we use, we want to explore different potential applications. And for each application, okay, we need to optimize, okay, the synthesis condition. Okay, we want to find out what's the best synthesis option, like the temperature and the synthesis, the time. Okay, we need to complete the chemical treatment. Okay, and of course we also need to figure out the cost. Okay, and how much cost we are going to increase if we use additive, and also how much performance enhancement we can achieve. Okay, of course in life cycle point of view, to conduct the LCCA and the LCA analysis. Okay, to provide more quantitative information to the decision makers for them to decide whether there is some material we can potentially use. Okay. So I think with that I'm done with my presentation, and so here you can see two pictures. This one was taken the last day when I worked at HR without the boss. The boss is in the office here. I think you can still see some familiar face here. And yeah, this is my current group working at the Hong Kong Polytechnic.
That's my twin sister.
This, yes.
I mean, it's about time for it.
Everybody was actually working in the lab, I think, before taking the picture. So yeah, so. What was that?
I didn't hear that.
Yeah, that's all for my part. Thank you all, and
right,
I'll be glad to take any questions.
We'll take questions. Yes.
I have a question. So for the PET modified binder,
Yeah.
What's the ratio of the PET additive? And
Yeah, it's I should have mentioned it's 2% right now.
So did you study the effect of the ratio on?
Yes, we did some preliminary tests before we use this percentage. Okay, because as you can see in my presentation, if we add the PET additive, it's gonna kind of increase the viscosity. Okay, it's slightly gonna increase it. If we add too much, okay, that probably will make the workability issue a problem. Okay, and also we found beyond the 2%, okay, the effect, the modification effect will not be further increased much. So we, for the preliminary test, we decided to pick the 2%. Okay, especially for the moisture damage resistance, we tried 2%, 4%, and different percentage. We found that at 2% we can already achieve a very good moisture damage resistance improvement. Okay.
Thank you, Doctor. By the way, so very good.
Thanks. Thanks. Yes.
Yeah. I don't know. I guess some of the discussion led me to believe it wouldn't have been better. But did you look at any applications where you would apply the additive to the HMA, like in the mixer rather than in the binder?
Yeah. That's a very good question. Actually, for this additive, we can do both. Right now, we haven't completed the test for the mixture yet. But this additive can actually, we can do it either wet process or dry process. Both can work because for this additive, it's kind of a solid in solid state at room temperature. But if it heat it to around 60 degrees C, it will become liquid. It's kind of just like the sassabate.
Right.
Yeah, just kind of like so. No matter we add it to binder first to modify the binder, or add it during the mixing of binder and aggregate, they should both work. Okay. Yes, Dr. Heim.
Thanks for the presentation. My question is, why is it okay to assume that in the DSR the threshold to evaluate the rotting and the fatigue are applied also for, to the mixture of the binder plus the plastic?
So you're talking about DSR test results?
Uh-huh.
So
why the thresholds to evaluate the performance of the binder? Why is it okay to assume that the thresholds to evaluate the binder also apply to the mix of binder and the PET?
What was your
what?
question again?
Yeah, Professor also didn't. Professor also didn't get. What's the exact
when you do the DSR,
Yeah.
Yes.
there are some thresholds for you to check the rotting
Right.
and the cracking.
Mm-hmm.
So why those thresholds are also
Why?
valid
I see.
for
Now you're
the binder and the mix of the binder and the PET?
I haven't
You understand the question?
You
Yes,
got
the question.
Yes.
The question, you said that when you are looking into the DSR testing,
Yes.
you have, let's say, the 5,000 as the threshold that you are using for the rutting. Now, when you are using an additive, why you are considering this is your threshold? That's the question.
Okay. So here we actually I didn't talk about the threshold. So we actually simply compare the testing results, the G star and the phase angle. So we simply check the values for the G star, whether it's increased or decreased. We didn't touch the threshold value. So we just present our results based on the rotting factor values. We didn't see it past certain threshold value or fail certain threshold value.
Yeah, I mean the thresholds when they are established, they were established based on the load and environment conditions that you have, and it's not for the materials. So the materials should meet these thresholds in order to perform well. So I think you don't need to change the thresholds because he's improving the materials to surpass the regular binder by keeping the thresholds the same, right?
Yeah. I think threshold value is made by someone, but this is just something objective. Threshold value is something subjective. So.
But the thresholds will be, let's say, for example, I'm not sure if you're using super papering. So adding PET, first of all, whether it changes the grade or not.
We're not talking about
because
grade.
These thresholds will change, because let's say if it's initially to start with, let's say it's a 6422, but when you add PET, let's say it stiffens the binder, it becomes
Yes.
70 minus 42.
Yeah.
So in that case, at 70 degrees Celsius, this rating value will be tested at 70 degrees Celsius, and the threshold will be at different temperature to be matched compared to 64.
Yeah, that's what I said. It's temperature and load. So, for example, if that case, you will switch it to a different temperature.
Right.
Since they are tested.
Yeah, here we did test different temperatures. The original binder, virgin binder grade is 64. It's it's non-modified. So we did test different, but we didn't touch actually the threshold value, which temperature grade it is. Actually, in Hong Kong, we are not adopting. We haven't adopted the super paper.
Yeah.
We partially adopted. Like for PG76, we don't have a dash. We don't have negative 22 or something. We just have PG76 because we are not worried about its low temperature grade. So it's kind of partially adopted in Hong Kong. Okay, so here we just want to use the super paper binder test to show how it can change with different performance properties.
Other questions? Yes.
Yes.
I was wondering if you've combined the PET, which is the wrap binder, because when you mentioned rejuvenation and when you're comparing these binder combinations,
Yes.
that decline, the FTIR, is because you have a virgin binder relative to the wrap binder, right?
Yeah. Actually, I think.
So like the absolute rejuvenation, if it's just PET and the wrap binder itself, have you guys done that?
Actually, you made a very good point. Actually, we did this year. We didn't present the one with the wrap binder. Let me see. Yes, we do have it actually. This is the wrap binder. Yeah. We don't have the 100%. Okay. So what we can compare here is the one with a different percentage of wrap. Okay, and the pure wrap only, okay, and pure wrap. But yeah, you are right. We didn't directly add the PET modifier into the wrap, okay. But still, if we compare these curves, we can still see the change of these peaks, okay. So these three, they are with the wrap binder. This one is without any. This one is PET, PET modifier, yeah. So we can still compare them, but I think you're right. We can just directly add the PET additive into the wrap binder without any virgin ones. Okay, but I think here we can already see the effect. But if we directly add the additive into wrap binder, I think it's more obvious.
Other questions? I have a quick question.
Yes.
I think, I'm sorry. Go
I
ahead.
have a question.
Yeah.
My question might be just a stupid question.
No question is stupid.
Okay, as I can see, the result from VBR and DSR is good, but since this is the modified binder,
Yeah.
do you consider include MSCR test in your experiment?
Yeah.
Maybe by including the plastic, it will reduce the recovery rate or something like that.
Yeah. I think we did do some the multiple stress the MSCR test, but probably it's not here. Okay. So here is, as I mentioned, it's kind of still ongoing study. We are what I have presented is the results we have. The test we have completed and the results we have already summarized. Okay, so we do have a lot to do actually. We do have many things to do, including the mortar test and the mixture test. Okay, right now we are still staying at the binder level. Okay, even the binder, as you said, we are still running more tests. Okay.
Okay.
Yes.
My question was on the manufacturing process for the additive.
Yeah.
Is that a hazardous process? Is there hazardous fumes or anything that comes out?
No. That's this is actually basically everything is done actually is in something kind of a seal. Okay. it's not a kind of something open to the air. Okay, so even there's something actually it will not be released to the outside. Okay, and actually this process, what happens is just there's no additional material generated. Okay, what we have is a PET, the amine, and this the product. There we will add extra amine material. Okay, so those amine material which is not reactive, we were going to save it for the next round of reaction. Okay, so we actually don't expect any additional products generated. Okay, so if there's no additional product, we don't expect there will be any kind of hazardous material produced during this process.
Yeah. Other questions? I have a quick question now.
Yes.
When we are getting all these waste materials, do we separate them? Because when it comes to like polyester or polyurethane, I know where these are the temperatures can be 350 and this material is still solid and they are not melting. So in that case, they will be more like fillers in the asphalt concrete rather than an additive. So I just wanted to see how they do the process of separating these materials, maybe.
Yeah, I think usually I know where your question is from. This is actually why we want to work on different waste plastic.
Right.
Yeah, this is the reason. Actually for those people who are treated with the waste material, they don't want to do the sorting. They just put all in most cases, they just put all different types of waste plastic together. You got the bottles, you got the plastic bags, so everything is mixed together. So,
like the PVC, I know that it has a very high temperature.
Yeah,
I work on welding PVC, so you need very high
we use
temperature.
it as a mold in the lab for the wall mix project.
That's true.
Yeah.
You put the mix in it, and it will be still.
But
right?
Yeah, but if we use some amines with PVC, if we heat it, it will be also degraded with time. Yeah, but it's better first cut it into small piece before we conduct the chemical reaction. Because if you just dump the whole PVC pipe, it will take too long.
So this is just to come now. So we
we are actually already completed some tests. We got some postdoc. Actually, I got one postdoc who's working on this. He did his PhD actually on this with chemistry background. Yeah.
Right.
So and also for PVC, it's actually poisonous material. So we need to be more careful to treat poisonous parts. And also the mixing and sorting. Yeah, it is a problem because right now if we just do with the PET, we expect we can get only the bottles. So that's actually very difficult in practice. Okay. So we want to know for the same process, what's going to happen for PE and probably PVC, and also we're going to try mixing them together to see how that's going to affect the final product. Okay. And then we can probably evaluate what's the significance, how significantly the mixing of different plastic will affect the final product. Okay. Right. So this is to come, something to come. Okay. Yeah.
Any other questions? All right, thank you so much.